Okay, welcome again, everyone, to another AstroAI lunch seminar. We have today Nicolò Pinciroli, who is a student, a graduate student in Politecnico de Milano, and he's also a pre-doc with AstroAI. He's also affiliated with INAF, and he's going to tell us today about making discoveries with multimodal astrophysics. Nicolò is around today. He's leaving to go back home tomorrow. So if you want to chat with him, catch him today. The floor is yours.
Okay, so thank you for having me here. And this presentation is about some topics about my PhD research that I'm going to finish soon, hopefully. And the title is Making Discoveries with Multimodal Astrophysics, because the main focus of my PhD thesis is indeed multimodal astrophysics, and I had the opportunity to work on this topic both here at CFA with the AstroAI group and in Italy with the group I'm part of. Okay, I have to go here. Okay, so I'd like to introduce the challenges. So, as many of you know, in astronomy and astrophysics, we have a lot of data. We already have a lot of data, vast amount of data, and we are going to have an even greater amount of data very soon with the LSFD survey that, if I'm correct, has just started providing some data. So, of course, it is not possible, even right now, it is not possible to analyze all of this data by hand. And this is the reason why we need to have automated methods. For example, we need machine learning, neural networks, and other tools, other techniques that can perform automated analysis that cannot be performed for all of this data by hand. And so the first part of this presentation is about the analysis of X-ray spectra. And I will show that X-ray spectra are interesting. We have also a lot of archival data from the Chandra catalog, X7 Newton, and so on. So we have a lot of spectra that we can take from the Chandra catalog, and we have some physical information, for example, physical quantities and also classes of objects for at least some of these spectra. And these are interesting because these spectra contain some of the information about X-ray sources. Of course, they're not complete. And this is the reason why it is useful to enhance these spectra with additional data. In this presentation, I will show how they can be enhanced with textual data about the source we are considering. Then what we see by enhancing this spectra with textual data is that we can also find a set of outliers that for some reason are different than the majority of other X-ray observations we have. If you look at the list of outliers, let's say the top 1% outliers in the dataset I'm going to present, then you see, for example, there is a gravitational lens system. You see, for example, there is a candidate pulsating ULX, and so on. So not all of these objects are necessarily anomalies. We don't know yet. But for sure, these are objects that are quite rare, that are quite interesting to study. So the second part of this presentation is about gravitational lenses, which are relatively rare. So only a few have been confirmed, I think in the order of hundreds, even less. And in particular, what is even more rare is gravitationally lensed supernovae that are even more rare. Only a few have been confirmed so far. For this reason, we need to use simulated data rather than real data, because we don't have the real data yet. But in the meantime, we can design a pipeline that can handle this data, independent of the fact that they are simulated or real. And to do so, again, we can use multimodal deep learning. Multimodal because if we are interested in seeing gravitational lenses, we can see this from images because we see the shape, let's say, of a gravitational lens, eyes and crosses, and so on. But if we're interested in seeing gravitationally lensed supernova, for example, then we also expect to have some brightness variation through time. And this is why we might need time series about that. So given a sequence of images, we can obtain, for example, a single image in 4 channels in this data set. that is the average of these images, and this should be useful to see whether there is a gravitational lens or not. And then we have the time series, again, 4 time series because we have 4 channels for the brightness variation. This can be obtained from the central part of the sequence of images. And the advantage of this network that I'm going to present is that it is quite lightweight. I trained these on old GPUs that were already old at the time. And in this way, so you don't have to handle a sequence of images that is much that is much work, that is much less efficient, let's say, to train, because it is much more expensive to train. And then the step forward that you can do is counting objects. So object counting is something that is not very common in machine learning for astrophysics, as far as I could see. But the idea here is that even if you have either unimodal data or multimodal data, it is possible to see not only how many objects you have in that image or multimodal data or whatever it is, but you can also divide these objects by type. So you can see, for example, 1 star or 2 stars plus 1 galaxy and so on. And this might be useful for future studies because you have these images, for example, or this multimodal data. And given the image, you don't consider only the central object that should be the main object, but you can also collect some statistics. If this works on real data, you can collect statistics about the background objects as well, and this could hopefully this can help counting stars, galaxies, and so on. So what are the research goals and contributions that I will present in this presentation? So first of all, the first step is compressing the X-ray spectra from Chandra, the Chandra catalog, into physically meaningful latent spaces. So the idea here is that we want to compress this latent spectra, this Chandra spectra into vectors that are very small and that are able to capture the most important information about the shape of this spectrum. And I'm going back to this very soon. So what we obtain is a so-called latent space, in this case, an 8-dimensional latent space, in which each spectrum is transformed into an 8-dimensional vector, basically, so a point in 8 dimensions, if you prefer. And once we have this latent space, we want to see whether this latent space makes some physical sense. If there is any correlation with some physical variables, if there is any correlation with classes, for example. And so this is the first part. But what we can see is that, as I was mentioning, spectra are not enough to fully describe an object, because an object can have different information in other bands. Maybe we can have additional information in the optical band and so on. So what we do is enhancing this spectra with textual sources, that is, summaries of scientific papers. And from this, we obtain another latent space that is, I would say, better organized. We see again that this latent space is correlated, has some correlation with physical variables, some correlation with classes, and so on. And finally, what we can also do is outlier detection on this latent space. And as I was mentioning, what we can see is that some of the rare objects are candidate pulsating galaxies and gravitational lens systems. So from here, the last part of this presentation that is about the classification of gravitational lens systems and the counting in images and actually multimodal data that contain gravitational lenses and gravitationally-lensed supernovae. Before going to the main part, I'd like to give you a very quick background about the main tools used in this presentation. So the first one that I already mentioned without actually explaining it very well is multimodal deep learning. So what does this mean? This means that we have multiple modalities about data, and these multiple modalities are, for example, images, time series, spectra, texts. So these are different kinds of data, different types of data we have about a certain observation, for example, a certain astronomical observation. In this case, this is the network that I'm going to present in more detail soon about for the classification of gravitational lenses. And in this case, we have the first modality that is an image, the second modality that is time series. In the case of spectra and text, these are two different modalities. And in general, we can have as many modalities as we want. There are some works with three modalities, for example. And we know that multimodal deep learning is effective in many fields. For example, in astrophysics, recently there have been many papers about this. There is a subgroup of AstroAI about multimodal astrophysics, multimodal artificial intelligence. And also this is effective in other applications. For example, in remote sensing, it is effective because we can look at images and we can also look at time series that describe the variation of something in the data we have. And so as I was saying, so multimodal deep learning is a sort of container that contains many different techniques. One of them is representational learning, and another one that is very closely associated is contrastive learning. So in representational learning, our goal is taking our data, our raw data, our astrophysical observations, and represent them using usually a small latent space. For example, an 8-dimensional latent space or 64-dimensional latent space, you choose the size. And for contrastive learning, I would say this is one step forward because once we have a latent space for different modalities, let's say in this case, summaries from papers, so text and X-ray spectra, once we have this information, we can try to combine this information using contrastive learning that I'm going to present in more detail. But the idea is very simple. So you have two different latent spaces in the beginning. So two different types of compressed information from two different sources. And what you want to do is putting them together. So you use a contrastive loss. In this case, it is called info and C. There are also other contrastive losses. And the goal is to put the matching couples together and put in the couples that shouldn't match far from each other. In this specific case, for example, let's say that we have a scientific paper, and for each scientific paper, we have, of course, an object, let's say, an astrophysical object, and then for each, we also have a spectrum. So let's say that for each scientific paper or for each scientific summary, we have a one-to-one correspondence with the spectrum. You can do this with the sources you like. You can do this with the modalities you like. So in this case, we want to match a paper with the corresponding source, a source with the corresponding paper. And if you have a paper that does not correspond to a source, we want to put these ones far away in the resulting final latent space. That is a shared latent space that puts this information together and has the same dimensions as the two input latent spaces. Now, what we want to do is seeing whether this latent space, the final latent space, is useful in some way, of course, because otherwise it doesn't make much sense to have it. And of course, we also want to see if it makes sense from a physical point of view. And for doing so, now I will use this thing that I have never to use. Okay. To do so, we can use physical variables in the green boxes you see here, and we can see the correlation between physical variables and latent space dimensions, which is the same thing we can do also with representation learning. And these are downstream tasks. So these are ways in which we can test whether our latent space, independently on how we obtain it, makes some sense. So for example, we can use regression, and there are many ways of doing regression. So we can have linear regression, for example, to see whether we have a linear correlation, a linear relationship better between the latent space and some physical variables. Or we can have even something more advanced that I'm going to show in more detail, that is symbolic regression. So what is symbolic regression in a few words? Well, with linear regression, we look for linear correlations between a latent space dimension. So we have, for example, the 8-dimensional latent space, and a single physical variable we are interested in. With symbolic regression, we can combine these physical variables together using mathematical formulas. So, for example, we can sum these variables, we can have ratios between these variables, and so on. And this is done automatically, so using the symbolic regression algorithms. And then another downstream task that I already mentioned several times in this presentation is outlier detection. In this case, it is much more difficult to validate outlier detection outputs, because if we are looking for outliers, of course, we don't know if what we have found is really an outlier or not, if it is a real outlier or not. So in that case, what I've done so far, but this would be another work actually. What I've done so far is looking for some of the objects that are in the most anomalous outliers, let's say, and see if they were somehow interesting. So again, I found the gravitationally-lensed system and the candidate pulsating index. That is the one I like the most. And now I will go to a more methodological part in which I show the actual architectures that I haven't, which I haven't done so far. So the first part again is about X-ray spectra. So when we have X-ray spectra from Chandra, we have, let's say, heterogeneous data. So the main difference between these observations is that the count rate values are different, and this might depend on the brightness, it might depend on the distance of the sources. So, of course, if we have a source that is very close to us, the count rate is expected to be higher with respect to the same source being far away from us. So these distance factors could introduce a bias. We're not very interested in this kind of bias at this stage. What we're more interested in is the shape of the spectra. So for this reason, what we do is normalizing the spectra from 0 to 1, in this case, in such a way that the neural networks will focus only on the shape rather than on the absolute values. And then and this is used also to avoid biases and to make the machine learning algorithm work more efficiently with the GPUs. So we resample these spectra using, in this case, 400 beans, rather than having a different number of beans in every case. And 400 beans is usually enough to cover all the spectrum, also because in the first part, this sampling is much denser, because empirically we observe that we have more data points for lower energies. And so this instead is the representation learning pipeline. So the pre-processing of the spectra is necessary in order to understand this spectra, let's say, to create the latent space. And you can see this pre-processing phase here. The next part is actually using the autoencoder that I'm presenting in the next slide is more and more details. But what the autoencoder does basically is very simple. So it takes an input, in this case a spectrum, it compresses it in a very small representation, and then it tries to reconstruct the original spectrum as well as possible, starting from the compressed representation. As I mentioned several times, now we want to see whether the output, the interesting output of the autoencoder, that is the latent space, so the latent representations, the compressed representations of the spectra, whether these ones make some sense. So to do so, we can perform clustering with 8 classes or 2 classes in this case. I will show the results soon. And we can also see whether there is a physical interpretation to this latent space. That means whether there is any physical correlation with some of our physical variables we already know we have measured about these sources. So this is the typical structure of an autoencoder. So we have in input, we have our spectrum. In this case, we compress it with an encoder. In this case, we compress it to an 8-dimensional latent space, which is small. And then we try to reconstruct the spectrum using a decoder that is more or less symmetrical with respect to the encoder. And finally, we obtain a reconstructed spectrum. In order to optimize the encoder, what we want to do is minimizing the error between the input spectrum, the original one, and the reconstructed one. But of course, the reconstructed one will be a smoothed and approximated version of the original one. I'm going to show this soon, because we are losing some information in the compression process. But we don't care that much about that at this stage, because it is true that we miss some of the details, but since we are more interested in the overall shape of the spectra at this stage, then I would say that it is fine, because as long as we are able to capture the overall shape, we are also able to find some correlations with some of the physical variables, as I will show. And this instead is the contrastive learning framework. So the contrastive learning framework starts with the results from the representation learning framework. As you can see here, we have the data embeddings that are basically the spectrum embeddings, so the compressed versions of the latent space. And in this case, I wanted to have a bigger latent space to capture more detailed information. And the idea here that I already introduced before is to have an alignment between summaries from scientific papers to an alignment with summaries of scientific papers and X-ray spectra. So I already introduced this. We used an influence loss, and we obtain a shared space that is 64 dimensional. Now, as I will show in the results, this is not, this shared space does not have a perfect alignment for many reasons that I will show in more detail. For example, one of the reasons is that our spectra don't contain all the information about the source, and the summaries are not summaries about the spectra only. These are summaries about the sources. So they might be summaries about the optical components, about many different things that are not captured in the spectrum. So I think it is quite expected that there is misalignment in some cases. So in order to perform the final physical interpretation, what we do is considering the concatenation of the post-alignment papers, the post-alignment paper embeddings, let's say, and the post-alignment spectra as well, because they're not perfectly aligned. They're not exactly in the same position. So this is what I actually already introduced. But the key point here is that by doing this, given a spectrum, we can look for texts that are close to this spectrum. So in principle, we could obtain a summary based on this text, even if I haven't done this yet. Or we can do the opposite. So given a text, we can look for spectra that are close to this text. And this will be part of future work. Now, as I was mentioning, one of the downstream tasks is outlier detection. We see that gravitational lenses are rare in this case. And this is the architecture of deep gravity-lens, that is a neural network that classifies multimodal gravitational lenses data. So as I was mentioning, we have an image and a time series. Actually, we have 4-channel images and 4-channel time series, so actually 4 time series. And we can also extract two statistical quantities from the time series that are the mean and the standard deviation. And in the results, I'm not showing this explicitly, but there is a small improvement, 1% over the final results. So each of the yellow boxes you see here, so LowNet, and MooNet, is a multimodal network, and each of them performs a classification. In this case, we have 4 classes, that is no lens, gravitational lens without a supernova, gravitationally lensed supernova of type 1a, gravitationally lensed supernova of type core collapse. So each of these networks performs this classification into 4 classes, and each of them outputs not only the class, but also a feature vector that comes from a previous stage before the final one, previous layer before the final one. And now we can concatenate these feature vectors, and we can perform, and yes?
Sorry, I think I'm just missing a bit the physical picture of these. So, are you claiming that you're using Chandra data to discover lens supernovae?
No.
Okay.
Sorry, probably, no.
So especially because I mean, you know that most of these lens supernovae are found in cluster fields. So like these fields will be dominated by the X-ray emission.
No, I didn't explain myself well. So the truth is that this second part of the work came first, and then I wanted to connect it with the first part of the work. Anyway, so there is the Chandra part about the analysis of outliers, and in that case, what I can see is that one of the outliers is a gravitational lens, not a gravitationally lensed supernova, as far as I know, but that is seen as an anomalous system. And that can be, that is a classification I find in the Chandra data, that it is an outlier with respect to the X-ray data. But for this second part of the analysis, I'm using simulated data sets that have nothing to do with Chandra. These are, for example, there is a simulated LSST data set. So in this case, you can forget about the X-ray data.
Thank you.
But this was just to say that one of the topics of this presentation is looking for some rare events, some rare phenomena, and so this is the connection between the Chandra outlier detection part that I showed before, and gravitational lenses that are quite rare, and gravitationally lensed supernovae that are even more rare. And I don't remember right now how many of them have been discovered. I think less than 10 have been confirmed.
Yeah, maybe
Okay.
like 10. But
Maybe
some
like
of them
10.
are
Okay.
Like,
So
yeah.
of course I could not use the real data for machine learning algorithm, and I had to rely on simulations that someone else did actually.
Okay, thank you. So for the Chandra part, when you mentioned that you basically want to classify any X-ray spectra found by the Chandra source catalog, how good is your classification for low signal spectra? Because I mean, you may know that for lens quasars that Chandra has looked at, sometimes the exposure is like very short, and you know the signal to noise statistic is not very good.
Yeah, the answer is that I didn't mention this, but in the data set I am considering only the ones with a high signal to noise ratio. And the reason is that if we have a low signal to noise ratio, we have also significant error bars, which I should account for when I use the autoencoder. So in this first stage, I didn't consider observations with a low signal to noise ratio, but I think I will do that in the future.
Thank you.
Thank you. This is useful because I want to use this for my PhD dissertation. So these questions are useful. Thank you.
I have a question. Anyone else has a question? I have a quick question. Maybe you said it and I missed it. Are you training each of these networks separately?
Yes.
Okay.
Yes, each of these networks is the yellow boxes is trained separately on the same data, of course, with the same split train validation and test set. And then I assemble the results, and the assembling part does not have fine tuning. So I just take the outputs of these networks, and then I take an SVM that can be run in seconds, literally, on this concatenation. And I'm not showing this in this presentation, it is in the paper, but what I saw is that GlowNet, for example, GlowNet is a fully connected network that takes this input multimodal data. And of course, as you can expect, since this is not a CNN, it is not a transformer, it is very bad. I mean, it is worse than the other ones. You could expect that a very bad network would not be very useful for this task. What I saw is that if I assemble all the networks, including this one, including the bad one, the results are actually good. So the results improve slightly, even if we include this bad network. And my hypothesis is that this happens because each of these networks sees the data in a different way. So I'm putting together complementary views of the data, which is why there is an improvement when I consider 3 networks in place of considering only 2 of them. And the advantage of this architecture is that, as I was mentioning, This is very lightweight. I run this on a 4 gigabytes GPU that is quite old and now has been dismissed because I didn't have access to better resources at the time. So this one for sure could be improved with more advanced architectures. But as I'm going to show in the results, actually I tried also another multimodal network that worked on the same types of inputs, so image and time series. There are not many works that combine images and time series actually, and this network was designed for remote sensing applications. It was much more complex, it was much slower, but for this specific task, it was not more effective for some reason. I think this is the reason is that in this multimodal data, we have relatively simple and small images. So we have a central object that is what we're interested in. So we don't need a very, very complex network to perform this task. Anyway, the extension of this is what I call the Hydra pipeline. Hydra because even if I am showing a single output here, you must imagine that this one is for counting. We have 7 different types of objects. So for example, stars, galaxy, gravitationally-lensed supernova type 1A, and so on. So we have 7 of them. So it has multiple heads, like the Hydra, the mythological Hydra. So I use this name for that reason. And the structure of these networks is very similar to what I had before. L counter, G counter, and M counter are very similar to the networks I had. And this pipeline is able to count objects, astronomical objects, inside this multimodal data. But in this case, as you might expect, as I'm showing this in the results as well, as you might expect, the main contribution is given by the images and not by the time series, which are still useful for transient objects anyway. So there is a slight improvement if we use multimodal data. And in this case, I think this is an interesting problem because this is counting objects. In this case, the counting is quite limited. We can have 0, 1, or 2 objects for each type. It is multi-output because we have an output for each type of object. And it is regression because we are estimating a quantity, but this is not a normal regression because what we want to estimate is quantities that are integer numbers. So the name of this thing is ordinal regression. The difference between ordinal regression and traditional regression is that in this case we have counts, we have integer quantities. And the other difference with respect to classification, for example, is that with ordinal regression, in the loss function, we account for the fact that we are having counts. So basically, if we predict 2 and the ground truth is 0, we have an error that is bigger than predicting 1 in place of 2, for example. If you have traditional classification, you cannot do this because all the classes are the same. And indeed, ordinal regression in this case, if I leave everything as unchanged, is more effective than classification by, I think it goes 10% more or less for counting. Okay, now I will show you the results finally. So let's start again from the X-ray spectra. So in this case, as for the X-ray spectra, the first thing I did was performing hyperparameter tuning to see which model was the most effective one at reconstruction. And you can see these curves, these are training curves. The dark blue curve in the center is the average of these curves, and the gray curves are all the other training curves. You can see there is early stopping in some cases. So this is why you see the decrease of the blue curve in the end. And you can see that this more important to me, that all of these curves converge. So independently on the hyperparameters you choose for the autoencoder, you have a convergence towards a good reconstruction in some way. But well, of course, I chose the one with the lowest validation loss in the end. And you can see there is no overfitting as well, because these 2 curves, the train on one side and the validation on the other side, are very similar. So there is no overfitting. One thing I should have mentioned before is that in this data set, the train set, the validation set, and the test set are a bit different because the test set, the final test set, has probably a different distribution with respect to everything else. Because for the test set, we have a set of confirmed classes, we have a set of labels we know, while for the train set and the validation set, we don't have any of this information. So the distribution of classes in the train set and the validation set is probably very different. But this is the reason is that I wanted to exploit all of this unlabeled data anyway, because for reconstruction I don't care about the labels. And then I wanted to test on data for which I had the actual labels, for which I could study correlations and so on. And I could not use only the label data because we have less than 2,000. So it wouldn't have been probably a big enough sample for this task. So as I was mentioning, the output of this is a smoothed reconstruction. So the original points are the black points, and they can be interpolated with the blue curve originally. And if after the autoencoder, the reconstruction performed by the autoencoder is the red curve. So you see that this reconstruction in some points is apparently quite bad. I think this depends on the fact that, first of all, this is also an optical effect, let's say, because this is in logarithmic scale, and also because here, for example, in the last part, we have fewer samples because most of the samples we are using as the input for the autoencoder are in the first part. And also, I would say that the interesting thing is that the densest parts, the parts in which we have more information, are the ones reconstructed in the best way. For example, here, of course, this curve is not perfect because it comes from an 8-dimensional vector, but this follows the average. So I would say these curves reconstruct a smoothed version of the spectra as I expected. And this is instead a bidimensional representation of the latest space. So this is only for the test set for which we have 8 confirmed classes. This 8 is independent on the dimensionality of the latent space. It is just a coincidence. What you can see here is that, for example, this part here, that should be AGNs. Yes, this is AGNs. This part here, that is AGNs, forms a cluster. This is a t-SNE representation, but I'm going to show the results on the full latent space that is not compressed in 3D in the next slides. And this green part instead is YSOs. So in this case, you can see two things. That first of all, we have some classes, AGNs and YSOs, that are dominant, and they're separated quite well. And also that indeed this separation is relatively good. And also we have a small subcluster here that this is interesting because this is a subcluster of AGNs, and all of these points correspond to the same source, different observations of the same source. So it makes sense that they are close to each other, and they are isolated because they have different physical properties with respect to the main cluster. So this is why they are isolated, and but I won't give the full details now. This is the output for clustering instead with the 8 classes. So here you can see the ground truth classes, and here on the x-axis you can see the cluster predictions. As you know, clustering does not provide labels in output, it just provides a set of clusters. So how can we assign these labels? Well, there is an algorithm called Hungarian algorithm that basically maximizes the trace of this matrix that is balancing the balance accuracy, maximizing the balanced accuracy. And you can see that some classes are easier than other classes, for example, LM star. Some classes are more difficult, and there is some confusion between some couples of classes, for example, high mass X-ray binaries and high mass stars.
I have a good question.
Yes.
This is to me is counterintuitive. compared to the plot you just showed, where it looked like AGNs and YSOs were well separated, while CVs were all over the place. Is that?
Yes. So the reason why this happens is that, so you see here, YSOs are the green one. If we want to maximize the balanced accuracy, YSOs have the same weight as the other small classes, the classes that are not well represented. So this is why probably, so
No, I made a mistake. I thought of CVs actually, so that makes
okay. Good for me, because I didn't have a more complete explanation. Okay, so this is clustering with the classes. There is some confusion. We expect this confusion because of two reasons. First, the autoencoder is not trained on these classes. It doesn't know anything about classes. And the second reason is that the spectra of these classes are in some cases similar to each other. I ran some tests that are not showing here. They're in the paper I just submitted. But what we see is that the statistical difference between spectra belonging to different classes in this data set is not very significant. So they look very similar, and there is also a lot of variability between the spectra, among the spectra that belong to the same class. So this demonstrates that we can obtain some information even from spectra alone, also in terms of classes, but we need some additional information to perform a better classification and better clustering. A similar task is still clustering, but for two types of objects that are AGNs on one side and stellar mass objects on the other side. Stellar mass objects include high mass X-ray binaries, low mass X-ray binaries, cataclysmic variables, and isolated neutron stars. I hope I haven't forgotten anything. Anyway, you can see this is much simpler than what we had before, because we have two classes. They're also quite balanced because the stellar class, the stellar mass objects class is formed by four classes. And here the balanced accuracy is around 70%, while in the previous case it was around 40%. And we can also see that there is a correlation between the latent space and some physical quantities. For example, this is the hardness ratio that is related to the shape of the spectra as we expect. And this is my favorite part, because this is symbolic regression that I really like. And you can see there is a correlation between one of the latent dimensions in the latent space, this is the first one, and the ratio between the flux in the hard band and the flux in the broadband that resembles somehow a hardness ratio. It is not the same, but it resembles the shape of a hardness ratio. And you see that the linear correlation, this is the Pearson's correlations correlation rho that you see here, is relatively high. Well, this doesn't look very linear to me, but this is still relatively high. So this means, and this means that the latent space somehow encodes information about the shape of this spectra again. And with symbolic regression, we can find this formula in an automated way. Okay, now going to the contrastive learning part, I would say this is one of the main results. So this plot might be a bit small and hard to read without an explanation. So this is why I'm here. So here we have two axes, the x-axis and the y-axis. So what we want to measure is the recall at k%. So imagine you have a spectrum, for example, and you want to find the text that represents the corresponding observation with respect to that spectrum. After we have done the contrastive learning part and all the alignment, then we expect the corresponding text to be very close as possible to that spectrum. So what we do is taking the test set, taking a single spectrum, and looking for the neighbors of this spectrum, the texts that are closer to this spectrum. And we see, for example, we take a neighborhood that is 1% of the latent space, that is this k here on the x-axis, and we see in how many cases we find the corresponding spectrum, the corresponding text. And this is the recall at k%. And in this case, if we take the 1% neighborhood, we see that this value is 20%. So we find the corresponding text in 20% of the cases. If we take the 10% closest neighbors, this goes up to 70% and so on. So of course, this is not perfect because spectra and textual summaries don't contain the same information, so it is quite difficult to align them. But this shows that this latent space, the shared latent space, has some alignment that makes some physical sense. So it has learned something that is not a baseline, because that baseline will be a straight line with 1% for the 1% neighborhood and so on. And these instead are the correlations between the enhanced latent space, so the final latent space we have, and some physical variables. So you see, again, we have, for example, good correlations with the hardness ratios and with some of the parameters of spectral models as well. And this big table instead represents the regression with respect to our physical variables. So in this case, what we do is taking the latent space, we use k nearest neighbors with 3 neighbors. So what we try to do is to estimate for example, the hardness ratio or any of these physical variables based on the 3 closest neighbors, because this is a way to measure, to see whether our latent space is well organized. And what we can see briefly is that if we consider the post-alignment latent space, we have often a significant improvement with respect to the best of the 3 alignment latent spaces. So combining spectra and text and aligning them means that we are also able to obtain a latent space that is well organized with respect to physical variables, so we can make predictions about these physical variables. There are some exceptions. For example, bar prob B is one of the exceptions because it has to do with the temporal variability that is not captured well in spectra. And then we have these that are parameters for the APEC model. But in this case, I would say that this difference is, even if there is a negative sign, so there is no improvement in this case, I would say these are not statistically significant because these are within the uncertainty interval. So it doesn't improve anyway. So in this case, it is useless to make the alignment, to perform the alignment, but it is not something significant from a statistical point of view. This one is instead. So in this case, if you are interested in var prob B, don't perform the alignment because it is going to give you wrong predictions, worse than the ones we have. And then what we can do is also outlier detection that could be transformed in the future in real anomaly detection. But for real anomaly detection, we need maybe some models about sources, and we need to compare to make additional comparisons. As I mentioned several times, from this we see that we can find, for example, pulsating ULX, ultraluminous X-ray candidate pulsating ULX. And this is very nice to me because this is another research I'm doing. This paper was, the results from the other paper were not included in this data set because I wrote them and I wrote them afterwards. And so in that paper, I find that this ULX could be a pulsating ULX. And from this one, I find that it is also an outlier. So it is something strange. Maybe it is not a pulsating ULX. So this is nice to me because it means there is something strange that maybe we want to investigate more. And this plot instead, so here each of the numbers is a different class in the contrastive learning data set, but the individual classes are not important here. What I wanted to test here was whether the anomaly score in some way depended on the abundance of objects belonging to a certain class, and the answer is no. There is not a significant correlation, as you can see here. Now, going to the results for gravitational lenses classification, what we can see is that with this network, we are able to improve the state-of-the-art results up to 36% with respect to unimodal models. And this one, deep gravity lens, is the method we're proposing that is better than DeepZipper and DeepZipper 2 that are the main competitors that worked on very similar data. And SDNet, we trained on the same data, of course, that was the one used for remote sensing applications instead. And these ones are instead the individual networks. As I mentioned, GLONet, that is the fully connected one, is the worst, but still it gives a positive contribution anyway. And what we can see from the confusion matrix is that the main source of confusion, this is for one of the simulated data sets I used. So one of the main sources of confusion, of course, is between the two types of gravitationally lensed supernovae, because of course they're more similar to each other with respect to a gravitationally lensed supernova and no lens, because in both cases we have some variability in brightness, and we also have a gravitational lens in the image. So this is, of course, as expected, the main challenge. Now, I also tried with real test validation. This is not a confirmed gravitational lens supernova, but this was found by the Deep Zipper authors as a candidate a gravitational lens supernova. So here you can see this suggests the presence of a lens. This is a Reitenstein series. So, and you see some variability. So to me, it could be a gravitational lens supernova. And this network finds it again as a possible gravitational lens supernova. So this is consistent with previous results. As for counting instead, so the goal now is counting objects in multimodal data. And what we observe basically is that this depends a lot on the abundance of these objects in the multimodal data. Stars are very abundant in our data. And in this data set, instead, non-lens supernovae of type CC and 1A are not very common, while the lens ones are more common. But what these box plots show that the low results also depend partly on the data set we use, because these are for all the data sets at once. I hope I'm not spending too much time. No?
We're close
Okay.
to the end, and if you want to have any questions, then.
Okay, I will be very quick. So this depends on the quality of the data set, and it depends on the number of samples we have. And so this is what you see from this plot. And these are the quantitative results. I'm not going in detail through all of them, but what you can see is that the most challenging data set is the same as for the classification, even if I didn't comment this in detail. If we put all the data sets together, apart from this wide that has shorter time series, if we put all of them together, we obtain similar results. So we can have a big data set that includes data from different instruments and obtain similar results, which can be useful in case you want to analyze different types of gravitational lenses. As I was mentioning, the images give the most important contribution, but still we have a small improvement by including time series as well because of the transient phenomena. And I will go to the conclusions now. So what I've tried to show is that representation learning can transform our raw data, our raw observations into some compressed versions, some compressed catalogs that contain, that encode physical information. And what I didn't mention is that with the contrastive learning pipeline, we can compress the data in such a way that we are left with 3% more or less of the original size, still keeping a lot of physical information. And also that, these pipelines about gravitational lenses could be used also for LSST data as well. And what we can also see is that multimodal learning outperforms unimodal learning in the applications I've shown, and that we can again extract physically grounded representations, and we can start to automate discovery also thanks to algorithms like symbolic regression. This is one of the stages of symbolic regression. And future work can focus on many different things. One of them could be creating, for example, a chatbot, a conversational agent that is able to analyze this multimodal data, and in particular the spectral data. So thank you for your attention. And if you have any questions or you want to, and these are the QRs for the details.
Right. Thank you very much, Nicolò. Are there any, you have time for one quick question only? Anyone wants to go? Okay.
No, if someone has a question, I have the chance to ask. Okay, thanks, Nicolò. Could you speak like 1 more minute on how you did the symbolic regression or what your plans are?
So yes, so for the symbolic regression, the way in which it works is very simple because first of all, I took latent spaces and took the latent spaces that came out from the unimodal representation learning pipeline in this case. And so what I wanted to do was trying to see whether there was any correlation between these latent dimensions and combinations of physical variables. In my case, it was fluxes, because we can combine fluxes and obtain dimensionless things, for example, something similar to hardness ratio. And the symbolic regression, one of the main symbolic regression libraries in Python is called PySR, and it is based on genetic algorithms, let's say. And so it starts by creating a random formula that combines these physical variables. It looks at the correlation basically between this formula that it has extracted and the latent space, and then it refines this formula step by step, and this refinement leads to the final the final output, that is a formula with a hopefully good correlation with the latent space. And I think this is interesting. It has not been explored a lot in astrophysics as far as I could see. Symbolic regression in general, there are a few papers that have been peer-reviewed and published. So I'm right now I'm working on symbolic regression for time series. I'm trying to fit time series with symbolic regression for another project. So it is something I really like because I like to extract formulas from the data.
And we have an expert in the audience. So if you want to chat with Helen, maybe it would be helpful to Helen right there.
Nice. Hello.
Okay, sorry for putting you on the spot. Okay, well, we're exactly, well, we have 1 minute or so, but I think we should wrap up. But maybe I have a very quick question. So when you find that it's a very interesting result that adding, text, informing the model with the literature, with astronomical literature, enhances the classification. But so when you use it for inference, for example, do you always have to have the paper associated to the source, or can you just put the data?
Not necessarily, because
Okay, so you can have half of that vector and then
yes, absolutely.
Okay.
Yes. The results might be, so I can show you very quickly.
Very quickly.
Very quickly. It's difficult here because I have to press. Oh, it was. So the best column here is the post alignment both, that is the concatenation of spectra and text. If you have only the spectra, you just take the post alignment spectra column, and these are the predictions you can make that are quite similar.
That's good. Okay, well, let's thank Nicolò again.
Thank you.